So back again with another episode. So in this episode, we're going to do AVL tree. So AVL tree is not something special. It's just the binary search tree with a special condition where we have to check the balance if that tree is balanced or not. I think it's in use case when you have a large data structure. So using AVL tree might save you a bit of time to go into a tree and look for data. So this is how like the real world use case of this method of the binary search tree. So yeah, before I'm going to this, so I want to specify one thing a little bit. The code that we're going to write here is not as different from the last episode of the binary search tree. So probably some of the functions I'm not gonna go much into detail about that because I think I have already like explained those operations and those functions in the last episode already, so I'm not gonna really go into full detail, but I will explain something new in this episode, okay? Like something that, needed to be explained a little bit before we go into further. So, yeah, anyway, let's get started without me fussing around too much. So, first of all, as usual, we're going to have, and again, I made my first mistake, should be struck notes, so we need to have something to store our data in the nodes. So yeah, so first of all, we're gonna call this in data. Again, we're not gonna work with generic function. Last time I worked with generic function, but this time just want to simplify my code a little bit. I can't talk, so I'm sorry. I have to simplify our code a little bit to make it more user friendly, I guess. So yeah. So I'm not gonna explain this thing, which is like creating pointers for left and right child. But this is something new. We have to create our height. Okay, so we have to keep track of the height of the tree. This height equals to 1. So we have to initialize the height of that tree to 1. This is our first thing. So the second thing we have to do before we are going to do the insert function is we want to have the height function, which we need to get the height of the tree, of course, and also to get balance as well. So getting balance basically get balance of the function, which needs the help of the height function as well, because you have to calculate the I think the overall balance of the tree. So the formula should be the height of the left subtree minus the height of the right subtree. So anyway, int height. So we're gonna pass down the node and we're gonna call it node. For some reason height. Sorry, this is not Java. Okay, I keep on writing this dot. I mean in Java, there's no pointer right here, so have to be a little careful. So we're going to check if that first of all have to check the base case. Okay, if the node that we passed in from the parameter is a null, okay, and then what we do just return 0. It's nothing to be done here. And then if it's not, then just return the node and then pass it to the height of this node, okay? And then we're going to have a function to get the balance of the tree. So to get the balance of the tree, um, we need the height. Like I said, we need the height. So we're gonna the node inside it. So and then we have to create not really create, just check the same thing as well. If the node is null, then if it's not null, just return the height function that we did earlier of that node from the left subtree of that node, and then minus the height of the right subtree of that node. Okay, that's all we have to do. That's all it is. So after this, there's still two more functions we have to do though before we get into insert. Not just only these two, we have to get the rotation as well. So we have to like check if there's some point we have if there's some point that the tree is unbalanced, and then we check the balance. After we check the balance, if it's unbalanced, we just have to rotate some of the nodes, right, to make it balanced. So we need to have function to rotate the node to the left. Okay, so right or left doesn't matter, so whatever you do first. So we're gonna do left first. Okay, left rotate, we're gonna call left rotate, and then we're gonna pass in the node of X, gonna call it X. So X is going to be the left, Y is going to be the right. So remember that. So in the left function right here, we're going to create a variable Y, which is the right one, okay? And then store the, yeah, the current node, the right child of the current node to a variable called Y. And then we're gonna create a temp variable as well to store that left child, okay? Left child of the current node. And then we're going to perform the rotation after we created the variable. So we're going to have the left assigned to X, and then we're going to have the right child of the current node assigned to the temp, okay? And then we're going to update the height after we've done that. So we have to update the height. So X, we're gonna do the left side, okay? Equals to 1 plus, and then we have the max function. We have to find the maximum value, right? So maximum value of both the height from the left side. Oops. So X to the left, and then you minus the height of the X, the right of the X. And then same thing here. Oh, this is not minus. I don't know what was I thinking. This is comparison. This is not doing any plus or minus operation. Sorry, okay? Anyway, after we update the height, we have to return that root. Return Y. Okay, so the right one, I'm just gonna duplicate this one. It should be like almost the same thing. You just have to change the Y to X and the X to Y. The right to left and left to right as well. So I want to specify one thing. You see the 1 right here, right? This is to basically just add 1 to the current node. So if you don't add this, for example, if it's finding the max of each the height from the left and the right child, if they say if that node doesn't have left and right children at all, it's going to return 0, right? So the height should be 0. It's not true, okay? So you have to plus 1, which you have to accommodate the current node as well. So that way it makes more sense for the reality, you have to count the current node. So that's why you have to plus 1. Anyway, so after you made all of these 4 functions, which the height, the balance, left and right rotate, so now I think you're safe to do the insert function. So yeah, this is a new thing that I didn't do it last time. This is when we have equal key, right? Which means if you insert 6 and then if you insert 6 again, you're not gonna allow to do that. Just return the node for the user. This return node is not different, okay? I mean, it's not the same, okay? First one, you have to perform the BST operation first, okay? This is step 1, okay? Step 1, this is operation first, okay? And then this is when it gets something new. It gets to something new, okay? Second, you have to update the height, okay? This is really crucial, okay? You have to update the height. So we have node. Then you point that to the height, I guess. And then you will have same thing as this one. Just sorry, this one. So you just have 1 plus this thing right here, right? 1 plus and then find the maximum of each left and right height. So 1 plus std max function and then node point to the height of the node from the current node, left side of the current node, and then we're gonna compare to the height of the, sorry, let me fix this thing real quick, height of the right side of the current node. And after this, after you already like update the height, you have to get the balance factor to check if it's balanced or not. So I'm gonna call a new variable called int balance, and then I'm gonna go ahead and call the get balance factor. Gets balance, did I call gets balance? This thing should be get balance. Sorry, it's not balance, get balance. So get balance, and I'm gonna pass down the node. Okay, not the class node, just the object node. So if the tree is unbound, there are 4 cases to be considered. If the left all the left subtree is unbalanced, okay? So we have left, this is the first case, okay? Left case, and then we're gonna perform the right rotation. This is the first case, okay? We still have 3 more cases to go, so this is the first case. So if the balance more than 1, so this is depends the value that it comes out here. It depends if your get height function is basically just, sorry, the get balance function. If you're doing like some different, like you're get the right the height of the right and minus the height of the left, then the value come out should be different, okay? So some of the books may tell you to do things differently, but overall the concept should be the same too, so it depends on this one, okay? So if balance more than 1, which basically means the left is bigger than the right. If the left is bigger than the right, so it should be bigger than 1. So if the, or in another word, we should say if the left is heavier than the right, so it should be more than 1. So if it's more than 1, then we have to check if the key as well that we inserted to. So you have to navigate to the node and the left side, and then compare the data in that node on the very left side, just only left side the data, okay? And then you're just gonna perform the right rotate function. So we're gonna get the node, okay? And then case number 2, okay? Right case, which means the right subtree is heavier than the left subtree. So if heavier, then just perform the left rotation, okay? So it should be the same, just change the more than to less than. Sorry, this one you have to be a little bit careful. Not, it's still more than though, but because of the right is heavier, right? So if the right is more than the left, it should be negative. It should return negative number. This thing as well, if the key is more than the node to the right, and then data. So we have to get the data from the right subtree in the node, and then you do the left operation. And then here's the third one, okay? Third one, we call it like the double rotation, left, right case, okay? Then what do we do? So we're just gonna check if the balance factor, since we do the left first, so the balance factor should be more than 1. Just left is a little bit heavier than the right, so, and then we're gonna check the same thing as here. So this is the double rotation, okay? And I have to check if the key, same thing as this one. So I'm gonna copy this thing, I'm not gonna write it. Check this one. So for the double rotation, so we're gonna do the left rotation first, okay? So we have to navigate to the left of that left subtree of that node, and then reassign the left rotation to here, to the left, and then you're just gonna like return the right rotation after you done it, and then just note inside here, okay? Right, left case. So this thing should be the same. Balance is more than -1 since the right is heavier than the left, and then the key should be more than the data from the right subtree of that node, and then you're gonna like from here you're just gonna perform the right rotation, and then we insert the right subtree, I mean right node of that yeah, so right subtree of that node, and then we're gonna do the left rotation. All right, so that's done. So after you've done all this, just return the unchanged pointer. So I'm gonna copy the code here. So yeah, and then we're done here. So this is a lot to take in, you know, there's a lot to take in, but it's nothing hard at all if you know the concept, okay? Now let's move on to the function to delete a node from the tree. So before we do that, let me just implement another function to find the minimum value, okay? So I already explained the last episode, so I'm not gonna try to repeat myself here again, but I could summarize it a little bit. So basically, you just have to find the minimum value of the leftmost subtree. This is how you delete it, okay? When the node has 2 children. So now, let's do the delete function after we're done the min value Okay, so we're going to do the delete function. So this thing is not that different from the last time, but what's the difference is that like you have to check the balance of the tree right after you delete a node. That's what it is like so new about this. It's the rest of the delete function is the same as the standard BST one. So yeah, let's begin. Delete node. I'm gonna call this delete node, and then we're gonna pass down node, and then int key, the data that we want to be deleted. And then, same thing, we have to check if the if the node is a null pointer. This thing you could return a node or could return a null pointer because both are a node anyway, same as last time. If the key is less than the data inside the node, then you're just going to navigate to the left. Else if the key is more than the node and then data, and then just node to the right. Then when found, we have to check, okay, if the node of that left child equals to null, and also we have to check as well if that right child is also null. If you don't check, then if one of them has some value in it, then it might be trouble, check first. Then if the condition is met, then it is safe to delete. So just delete the node. Okay. Then you have to check another case as well. If the node has one child, sorry, one child, one child, either like left or right is null, so it doesn't matter. And then you have to check again if the node has two children. So if the node has two children, then you have to create a temp. Okay, create a temp variable and do the min value node, and you pass down the uh nodes. I keep on saying like I keep on writing like root for some reason because I keep on writing it. Okay, right, and then node, navigate to the key, and then set it to the temp to the key, and then after that just delete the recursion. Okay, delete node, and then you just do node to the right, and then temp key. Okay. This thing should be node. I keep on saying root again. Sorry, this shouldn't be key, it should be data. Less than temp of the equals temp key itself. Alright. Okay, so this is step 2 now. So step 2 is to update the height of the tree. So after that, we have to get the balance factor of the tree. So if the tree is unbalanced, same again, 4 cases. So first case should be the left case, which this is a little different, but bear with me, okay? I know this is a lot to take in, but bear with me. So we have to check if the balance less than 1, so if the left is heavier than the right. And also we have to check the get balance as well. We have to call a get balance function, and then we recur all the way to the left of the subtree, okay? And then you have to check first, compare them if it's less than or equals to 0. Okay, and then if it's true, then just return the right rotation. This is the right case, which means the right is heavier than the left. So we're going to get the balance factor if the balance more than um -1. No, this thing shouldn't be more than, right? I think it should be less than -1. Oh, sorry though. Sorry, this thing should be less than -1, not more than -1, less than. Because if the right is heavier, then um when you keep on minusing, then it's gonna get into more negative numbers. So be careful about that. I made a little mistake there. And we're gonna call the get balance function. Same thing. And this time around, just going to navigate, okay, to the right side instead, not the left. Okay, it's the right heavier than the left. Should be less than or equals to 0. and then we're gonna do the left rotation instead. So we have left and right case. Okay, so left and right case is the same things here. If it's left heavier than the right, then the balance should be more than one. And we have to check as well, get balance node, and then we navigate all the way to the left. Um, navigate to the left, and then if it's less than 0, okay, not less than equal, okay, be careful, just less than only. Then we're going to perform the left rotation. So we're gonna set the left rotation, left rotate, and then we'll have node point to the left side, and then return the right rotation after you're done. Return right rotation, just node only. So same thing as the right and left case, okay? The right case should be different. You just have to change a little bit of thing. If the balance less than -1 and get balance, and then you recur all the way to the right side if it's more than 0 or not. Okay, not more than or equals, okay? Just more than. And then you keep going to the right, and then you use the right rotate. And then you set it to the right. Oops. Right, and then you use the left rotate instead. Okay, if the right is heavier than the left. And then we should be done here, and the last thing is to return the node. Okay, that's a lot to take in, but I think it's fine. So I think we should be done with delete right now. Let's do a search function. I feel like this thing should be Boolean instead. I think Boolean. Last time I think I didn't do Booleans, but I think Boolean might make things a little bit easier. So we're gonna return false if the node is null, and then we're going to return true if it's found. Return true. You could do like a counter, but it doesn't matter here. So just Boolean will make things a bit easier for us. So this one you just have to navigate through the tree. So sorry, data not left. Bool. We're gonna call this thing while, I guess. I'm not sure what we call it, and we're just gonna repeat the search node node to the left, and then we're keep on comparing with the key. Okay, so and then we're gonna return value, and then this thing should be the right side. So the right side, you don't need to do much. I'm gonna declare a new variable called while as well, and then search node and to the right side. So just recur down the right side, just return wow, and then we're gonna have a void to check search, check if it's found or not. So same as last time, I have nothing much to say anyway. If found, just say it's found. Else, if it's not found, just say not found. And then we have to display the tree, right? So I'm gonna do it since they are asking for in order traversal, which is we have to display the left, root, and right. All right, it should be done now. Yeah, should be done here. Everything is done now, I guess. Wow, that's really a lot today. So, all right. First of all, let's do the function. So I'm gonna declare a variable called root, I guess, and then assign it to null pointer, initialize the null pointer, and then insert. So we're going to, in this time, since the picture right here, we have 1, 2, 3, 4, 5, 6, 7, and 8. I think I'm gonna use a loop instead for int I equals to 1, I guess. Then I less than or equals to 8. It's not 9, it's 8, and then I plus plus. Let's say we want to delete function, delete Let's say you're gonna delete the lead node at root, and then we're gonna say we want to delete number 3, I guess. I'm gonna do it this way instead. Like it's gonna be more efficient, I guess, so that we don't really need this anymore. So this is gonna be root BST. So this one, root AVL equals to insert AVL, and then we're going to, yeah, AVL and then AVL. Okay, so now we get it. This is delete, and then after that we display, and then just say search function, I guess. Search. Let's just say searching for 3. Same thing as this one. Searching for say 5. Sorry, this thing should be check search, not search node. Okay, should be the same. So it's AVL. There's 3 not found, 5 is found. So there you go. We did it. That's all it is. This episode, like, there's isn't much to talk about because most of the time, the functions are the same as BST anyway. They just you just have to add like a function to check for the balance, to get the number of height, to rotate left and right, and something like that's all you have to do in the AVL. It's just a branch of the binary search tree. Anyway, yeah. I guess we can end it here. So yeah, see you in the next episode, I guess. So I don't know. I don't know what the episode is gonna be, but anyway, we'll think of some project we want to do, but we'll always have projects, okay? So yeah, see you in the next episode and bye.